Okay, yeah. Wait. Yeah, okay, so the recording is not right. Yeah, I can. Okay, so we can start, right? Yeah. Okay, so recall that last time we were so okay. Last time we started looking at the MVB algorithm for, and this was a randomized algorithm for finding perfect matchings in graphs. So in the lecture before that, we saw a randomized algorithm using Schwarz-Zippel lemma to check whether a bipolar graph has a perfect matching or not. But that algorithm couldn't find a perfect matching. Okay. So last time we started looking at this algorithm, which can find perfect matchings, but we only looked at sort of the baby version of it, which does the same thing. It just detects whether the graph has a perfect matching or not. And the reason we did this was because the analysis of the success probability of that algorithm. Uh, so in the analysis, there was something nice, some nice property about the value of the determinant, which we would use today to actually give an algorithm that finds the perfect matching. Okay. So let me just quickly recall what we were doing. Yeah. So what we are doing is for every edge E, let if XE is the corresponding entry of the two-tay matrix, then we are uh, picking a weight corresponding to XE, calling it WE, uniformly at random from the set 2n square, and computing the determinant of M, which is obtained from two-tay matrix by substituting X by 2 to the WE, right? And if the determinant is non-zero, we output yes, else we output no. So this was the algorithm we saw, and uh, we analyzed the success probability of it. And in the analysis, one of the facts that we noted was the following. So if the graph has a perfect matching, then isolation lemma would tell you that with very high probability, there would be a unique perfect matching with minimum weight. So let me call that unique perfect matching sigma star. Then the determinant of M would look like 2 to the weight of sigma star times some odd number, right? And this implies that the largest power of 2 dividing the determinant of M is weight of the sigma star, right? So this is what we saw last time. So do you have any questions about this or is this
Yes,
fine?
yes,
Yeah.
yes, yeah.
Okay, so let me note this as an observation. It's observation, okay, 2. Yeah, so this is the observation. And today we would use this to give an algorithm that finds the perfect matching. Okay. So the algorithm is as follows. The first 3 steps are the same as this. And so, like in the algorithm, I start from step 4. That's because steps 0 to 3 are the same as the ones over here. Okay. So what we have done is we have picked random WEs, computed the determinant of M, and checked whether it's 0 or not. Okay. if it's non-zero, then we proceed. So, okay, let me add that step. Okay, let me write it over there itself. Okay, no, it's better. It's better. Yeah, then do this. Yeah. Yeah, so we proceed only if the determinant of M is non-zero, because if the determinant is zero, then like with very high probability, there is no perfect matching. So we only proceed if the determinant of M is non-zero. And what do we do? So we find out W, the log of the largest power of 2 dividing the determinant of M. Okay, so how can we find this W?
Yes, so I do not remember, but then probably we took, I mean, we took the values of W from M number of the, I mean, from a set.
Okay. Oh, no, no, okay, so this
Right.
is capital W, right? So what we took from a set were small w's. So
Yes.
these sort of give us weights corresponding to x's. So the weight corresponding to x is 2 to the we. But over here, w is something different. So over here, capital W is the log of the largest power of 2 dividing the determinant of M. And observation 2 tells us that this is 2 to the weight of the unique minimum perfect matching, right?
Okay.
My question is, how do we find this weight of the unique minimum perfect matching? Because log of this number is just the unique minimum perfect matching, right?
Yes.
Yeah.
Yes.
Okay, so one way to do this is the following, right? You start with W equals 1 and see if 2 to the W divides determinant of M,
Mhm.
right? If it does, you increase the value of W by 1. So let's say if 2 to the 1, that is 2 divides the determinant of M, then you check if 4 divides determinant of M, 8 divides determinant of M, and so on, right? So you check that 2 to
Yes.
the I divides determinant of M,
Mhm.
but let's say 2 to the I plus 1 does not divide determinant of M, then you know
Mhm.
that, okay, I is your W, right?
Yes.
So this is one way to do it. Another way is just write determinant of M in binary,
Mhm.
right?
Yes.
And check how many zeros are there at the end of it.
How many zeros are there? Where?
So how many zeros are there in the LSB, in the least significant bits?
Okay. Okay.
Yeah, so for example, if anything with 1 0 is divisible by 2, anything with 2 zeros is divisible by 2 square, anything with 3 zeros by 3 2 cube, and anything with I zeros by 2 to the I,
Yes. Yes.
right? So you just find out how many zeros are there and that's it. Yeah, so you don't even need to do anything like this. Okay, so this can be done efficiently. That's the point. Okay. So now we have found W, we want to find the perfect matching, and we would do this iteratively. So we would set initialize a perfect matching to the empty set. So what's the perfect matching? It's a set of n many edges, right?
Yes.
Yeah. So we initialize the perfect matching to the empty set. Then what do we do is for every edge E in the edge set, let Mij be the matrix obtained from M after removing the ith row and the jth column. Okay. So Mij is the matrix corresponding to ijth minor.
Mm-hmm. Mm-hmm.
Yeah. Okay. So by the way, what does Mij sort of correspond to? So look at the okay. So the matrix M is related to the two-tay matrix. The two-tay matrix is related to the adjacency matrix, right? The bi-adjacency matrix.
Yes.
So we are removing some row and column from M. So let's see what removing that row and column from the adjacency matrix would do, right? So if I remove the
Mm-hmm.
ith row and the jth column from the adjacency matrix, what am I doing?
Yes, so ith row and so that connectivity. So basically, we are removing that connectivity. Say what is there inside the two-tay matrix? If you can recall me, because
Okay.
uh,
So you remember what the bi-adjacency matrix was, right?
yes. So that I mean I can understand. So if a bipartite graph is having say broken into the two subsets, say m into n. So then we were
Mm-hmm.
having say m number of the rows and n number of the columns there. So I mean then we could design a bi-adjacency matrix. And if we replace those values by some variable, I remember then we used to get this two-tay matrix kind of a thing.
Right. So
So
in
now,
bi-adjacency matrix,
yes,
there is the let's say my bi-adjacency matrix is A, then ai comma j is 1 if and only if there is an edge between I and j in E, right?
yes, right.
Yeah. So the two-tay matrix was obtained by replacing every one in the bi-adjacency matrix with a variable and keeping every zero as it is.
Yes,
Right. And M was obtained by replacing every variable x in the two-tay matrix by 2 to the WE.
yes, because of some calculation simplicity, I mean, for that thing.
Right. Okay, so
Yes.
we would see the reason for 2 to the WE today. So what we saw last
Okay.
time, 2 to the W doesn't make any sense. You can just put WE.
Okay.
So if
Yes.
you're only interested, we discussed this, right? If you're only interested in finding whether a perfect matching exists or not, don't do 2 to the WE. Don't do any of this. Just do what we did in the previous class. Put X equals WE, calculate the determinant, check if it's 0 or not, done.
Yes.
Yeah, the reason we need to do the WE is because of this observation, and we would see how that observation comes in handy in sets 8, 9, and 10. Yeah. So
Yes.
now let's get back to the question. So if I remove the ith row and the jth column from M, it's sort of like removing the ith row and jth column from the bi-adjacency matrix, right?
Yes.
Yeah. So what happens when I remove a row and a column from the bi-adjacency matrix? What does that mean? Okay.
So
Even
so
a
it
simpler
means that,
question.
so yeah, so it means that basically, so so on one side I have removed one vertex, and
Right.
on the other side I have removed possibilities of, I mean, possible connections which I is connecting to the vertices j in the other side, vertex j
Okay.
in the other side.
So, okay, yeah, 50% correct. Okay, let me ask a simpler question. What happens when I just remove a row from the matrix?
So that vertex has been eliminated. I mean,
From
from one side.
from L, right?
Yes,
So
yes,
when I remove a row, every row corresponds to a vertex in L. So when I remove a row, I have eliminated a vertex from L.
yes.
Okay, so what happens when I remove a column?
Oh, I see. Then if you remove a column, then it means that okay. So I mean all the edges which are adjacent to a vertex, right? All those edges will get removed. So all the vertices which are incident on the vertex say j, from
Hmm.
whichever vertex in the first set will get eliminated.
Okay, but this is also true when I remove a row, right? Every vertex connected to I would be removed. Every connection would
So
be removed.
yes. So then the vertex one is connected to which vertices? So the column means what? So the meaning of the removal of a column would be, yeah. So yes, I cannot think of that. Okay, what would be the impact of the removal of a column then?
Okay, so every row corresponds to a vertex in L, right?
Yes.
So what does every column correspond to?
So column corresponds to, say, if the vertex number one is connected to, okay, which all vertices it is connected. So the column
Okay,
will
vertex number one
correspond
in which
to
set?
vertex number one in the set M. And
L, right?
say, so I'm considering, say, row wise. So vertex number
Okay,
one is connected to whichever vertex in the vertex set J, right? So those
okay,
entries will
okay, okay,
become one
wait,
and
wait,
the
wait.
remaining entries
So
will become zero.
there is no vertex at J. There are two vertex sets L and R, right? I am removing the
Yes.
jth column. So what is the first? So yeah, you were saying that you would go over the jth column row wise, right?
Yes.
Okay. So now yeah, say what would happen. Okay. So every column corresponds to a vertex in R, right?
Yes.
Yeah. So every row corresponds to a vertex in L. Every column corresponds to a vertex in R. So if I remove a row, I am removing a vertex in L. If I remove a column, I am removing a vertex in R, right?
Yes. Yes. Yes.
Yeah. So
Yes.
like rows and
Yes.
columns are symmetric.
Yes. Yes.
So like yeah, there is no like I could have as well said that okay, every row corresponds to a vertex in R, every column corresponds to a vertex in L, right?
Mhm.
Yeah, yeah. So okay, so every removing a row means removing a vertex from L, removing a column means removing a vertex from R, right? So then what does
Yes.
removing a row and a column mean?
Removing one row and one column means removing a
Right,
vertex from the set L and removing a vertex from the set R.
right, exactly. So
Yes.
what we are doing is for every edge I comma j, we are removing the vertex I and j from the uh, from the graph, right?
Yes.
So now our graph is n minus one. Like so, in the left half and the right half, there are n minus one vertices,
Yeah.
right? And okay, yeah, okay. Let me go to the next step and then I'll explain why this makes sense. So what we do then is, oh, I'm calling this Mij and Me at the same time. So let me replace this Mij with Me. Okay, yeah. So we have computed this Mij. Now what we would do is we would compute the determinant of Mij multiplied by 2 to the WE, the like weight corresponding to edge E, and divided by 2 to the W. And if this is odd, then we say that E is in the perfect matching. Otherwise, we don't add E to the perfect matching. Okay. So this is what we do. Why we do this, I'll explain later. Yeah, because this is not at all obvious why this works.
Yes. Yes.
Okay. But so at least is the algo fine?
Yes. Algorithm is fine, and yeah. But then we could solve this problem using the previous algorithm as well. So why are we devising a new algorithm, and what are the benefits of this algorithm over the previous one?
Okay. So by previous one, do you mean this one or the one where we did not use isolation lemma and just replace XE by WE?
So the previous one, I mean, even before that, I remember
Okay.
that we solved it using the, I mean, then we determined that whether the value of the determinant is zero or not, and we proved
Hmm.
the, I mean, we gave a proof in both the directions, and
Right.
yeah, we could solve that problem. Yeah.
Yeah, so okay, both that algorithm and just this baby version of MVV only detect whether a bipartite graph is a perfect matching or not, right?
Yes.
They don't find a perfect matching for us.
Oh yes. Yes.
Yeah.
Yes. I remember.
So over here, these steps uh, find a perfect matching for us. Okay, this steps find a set which I claim is a perfect matching
Hmm.
because I haven't
Hmm.
proved that this is a perfect matching. Okay.
Yes. Yes. Yes.
Yeah. Okay. So like at least the steps are clear, right?
Yes,
Yeah.
yes.
Okay. So now let me give some intuition about what's happening over here, and then we'll move on to formal proof. Okay. So I remove. So yeah. So Mij is essentially obtained by removing a row and a column. So by removing a vertex from I and a vertex from L and a vertex from R, right?
Yes.
Now suppose that Ij, the edge Ij was present in the unique minimum weight perfect matching. Okay.
Yes.
Then after I remove the vertex, yeah, if I after I remove I vertex I and vertex j, in the remaining graph, whatever remains of the unique minimum perfect matching would still be a perfect matching, right?
So even after the removal of the I comma j, yes, it would remain a perfect matching, right?
Right. So what we are essentially trying to do over here is find if that thing is a perfect matching. So even after removal, I have a perfect matching.
So I mean, according to the common sense also, so if there is a perfect matching,
Mhm.
and if I remove one edge from the perfect matching, the remaining one would
Right.
also remain as a perfect matching only.
Yes, but okay. Okay, so over here you want to find one perfect matching, right? But
Yes.
let's say there are two perfect matchings. Then when you remove an edge from the first perfect matching and remove an edge from the second perfect matching, you in the resulting graphs you would have perfect matchings in both the cases, right?
Okay. Okay.
So in that case, you might end up adding two edges which belong to different perfect matchings in one perfect matching, right?
Okay.
Yeah. So we need to show that this is a perfect matching. It's not completely obvious why this is a perfect matching, right?
Mhm.
Yeah. Okay. So the claim is this: if G has a unique minimum weight perfect matching, then E is in the in this unique minimum weight perfect matching if and only if determinant of Mij times 2 to the We over 2 to the capital W is odd. Okay. So I'll prove this claim, but before that, let's suppose that this claim were true. Okay. Then my question is the following. The, does this claim being true imply that PM is a perfect matching?
So if the claim number 4 is right,
Hmm.
so then basically we are doing this check for all the edges which are there in P,
Right.
right? So yes, so if this claim comes out to be true, then eventually we would be returning a perfect matching. This seems okay.
Yeah. Why? Okay. So there is one more thing that's required. So the claim assumes that G has a unique minimum weight perfect matching, right? So suppose the
Yes.
claim were true and suppose G had a unique minimum perfect matching. Okay. Yeah. So let
Yes.
me call this perfect matching sigma or sigma star. So now what this claim is saying is E is in sigma star if and only if this is odd, right? And look at all the edges that I'm adding to PM. I'm adding an edge if and only if this is odd. That is, I'm adding an edge if and only if it is in this unique minimum perfect matching sigma star, right?
Yes.
So not only am I returning a perfect matching, I'm returning that unique minimum perfect matching,
Right. Right.
right? So now you see that this uniqueness of a minimum perfect matching sort of helps us synchronize things, right? Because if like didn't care about this uniqueness and we were merely doing what we discussed a couple of minutes back, remove an edge, check if the resulting graph is a perfect matching or not, add that edge to the graph to your perfect matching, right? In that case, edges from two different perfect matchings might end up being added to our set PM, right?
Yes.
Yeah. So now the way we are avoiding that problem is by using this claim. So now not only are we checking, okay, so what does it mean to say that okay, suppose I wanted to check that the resulting graph has a unique minimum, has a perfect matching, right? For that, all I needed to do was to check that determinant of Mij is non-zero, right?
Yes.
Yeah, because Mij is sort of the M for that matrix. So sorry, for that graph, right?
Yes.
And we saw that determinant
But
of M being,
then,
yeah.
Yeah, but then this time we are not interested only in knowing that whether the perfect matching exists or not. We are also interested in knowing the exact matching as such.
Yeah. Okay. So, but my point is this: if determinant of Mij is non-zero, then the smaller graph has a perfect matching, right? But that
Yes.
means that take that perfect matching from the smaller graph, add E to it, you get a perfect matching of the entire graph, right?
Oh, yes. Yes.
Right. Yeah. So one way of doing that would one way of doing of finding the perfect matching would have been just to check if this is non-zero. If yes, add E to the graph, right? Sorry, add E to
Right.
PM.
Yes.
But the
Yes.
issue with that is there might be multiple perfect matchings in the graph, and I might end up adding edges from all of them. So, for example, consider this graph. So there are two perfect matchings over here, right? One this, and this, and another this, and this, right?
So, I mean, which matchings are the perfect
Okay.
matchings here?
So
Which two?
okay, let me draw over here. So this is one perfect matching. This is another perfect matching. The blue edges are one perfect matching, green are the other, right?
Yes. Yes.
Okay, so
Yes.
now let me suppose that I remove this edge. Okay. Okay, sorry.
Yes.
Let me suppose I remove these two vertices, right?
Yes.
Yeah. Then the resulting graph. Oh, wait. I drew the wrong graph. Yeah. Oh, yeah. Okay. Yeah. Fine. 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 Yeah. So I remove these two uh, vertices. Now, because I'm focusing on this edge, right? Now, the resulting graph still is a perfect matching. This edge and this edge, right?
Yes.
Okay. So I would add this to PM. But now let's say I'm focusing on this edge. So I would remove this vertex and this vertex, right?
Yes.
But then the resulting graph has these four vertices. But there is still a perfect matching, right? This green edge and this green edge.
Yes.
So I would also add this to PM. So this blue edge
Which two?
and this green edge, this blue edge and this green edge both are added to PM.
Mm-hmm.
Okay, this blue edge we saw and this green edge, because when I'm focusing on this, I remove this, I remove this. There is still a perfect matching in the graph, right?
But then, how is it possible that I add both blue and green, both the edges simultaneously to the perfect matching? That is not
Yeah, okay,
possible.
so it is possible, right? Because if our algorithm was this, just this, check determinant of Mij is non-zero. When I remove this, I remove so when I was focusing on this, I removed these two vertices. There was a perfect matching in the graph. So with high probability, the determinant of Mij would be non-zero.
Yes. Yes.
So the check would pass. I would add this, right?
Yes.
Similarly, when I was focusing on this, I would remove this. I would remove this. There is a perfect matching in the graph. So with high probability, so with high probability, the check would still pass, and I would end up adding this to the perfect matching as well, right? Because my check passed.
But then they should not be added. I mean, how is that possible that
Exactly.
both? Yeah.
Yeah. So in fact, what in this graph, what would happen is you would end up adding every edge. Because what I did for these two, you can repeat the same analysis for these two and these two as well. So you would end up outputting all the edges if you
Yes.
did just that. Yeah, so that's why you need this 2 to the capital W, and that's why you need this 2 to the WE thing. Yeah, we haven't proved claim 4, but claim 4 shows that if you perform this check, then you are fine. Then you are adding only one edges from only one perfect matching. Okay, so is this fine?
Yes.
Yeah.
Yes, but yeah, probably I could not hear your last two lines properly. So I could hear at that point that yeah. So if I mean, this algorithm will allow the inclusion of both the edges, and which is not right, because if we continue like this, then
Hmm.
eventually all the edges will get included into the perfect matching.
Right. Yeah.
So
So
after that, what did you say? So that
yeah.
I
So
could
after
not
that,
hear.
I said that okay, that algorithm was performing just this check, but
Yes.
if we modify that check to this, then this claim tells us that we would only end up adding edges from one perfect matching, the unique minimum weight perfect matching.
Oh, how so? Why so? Why so? Why is that?
Oh, so I haven't proved the claim yet. So if
Okay,
this
okay,
claim
okay.
is true,
Yes,
then that's
yes,
what's happening, right?
yes, yes, yes,
Yeah. Provided a unique minimum perfect matching exists, which we know exists with high probability.
yes, yes, yes.
Yeah. Because of the isolation lemma, right? So now let's prove this, and in the proof we would see what's happening. Okay. So yeah. Okay. So element of okay. Should I do this only like this or that? Okay. So I removed this edge, and that means that I'm in a smaller graph where this is a perfect. Hmm, how should I? Okay. So let G prime. Yeah, so let G prime be the graph corresponding to Mij. This is just the graph obtained from G by removing ith uh, vertex of L and jth vertex of R, right?
Yes.
Yeah. Okay, so now if okay, do I want to do which iteration do I want to do first? So if E is in the perfect matching, then removing this would give me a smaller perfect matching, but the weight of that, okay, yeah, would be okay. Yeah, let me do it like this. So sigma prime is any perfect matching in G prime, then sigma prime union E is a perfect matching. Yeah, so like two observations. If E is indeed in sigma star, then sigma star minus E is a perfect matching in G prime. And also I can take any perfect matching in G prime, add uh, E to it, and that would give me a perfect matching in G, right?
Yes.
Yeah. So in fact, this tells us something more. Therefore, sigma star minus E is the unique minimum weight
No, but I have a little doubt here that
yeah
if we remove edge E from a perfect matching, say sigma
right
star, so and if there is another matching, say sigma prime, and if I
Mhm.
include this E into another perfect matching sigma prime, so where is a guarantee that I mean this would remain a perfect matching even
Oh,
after the
okay, okay,
inclusion
okay,
of
okay, okay.
G?
So okay, sigma prime is a perfect matching in which graph? G prime, right?
Yes.
G prime doesn't have ing.
G prime does not have this thing.
G prime doesn't have the vertex I in L and vertex J in R, right?
Yes, yes, yes.
Right. So sigma, what does sigma prime do? Sigma prime maps L minus I to R minus J, right?
Right, right, right.
So
Yes.
when I add ij, it has to be a perfect matching because no
Yes,
edge
yes, yes.
in yeah.
Yes.
So
I
yeah,
understand.
that's why we are not just okay. So we are not just removing the edge ij, we are removing I and j both. That's crucial.
Yes, yes,
Yeah,
yes.
if we
Right.
were just removing ij, you would be right. It won't be a perfect matching.
Yes, yes, yes.
In fact, it cannot be a perfect matching because I and j are still present in the graph. So the smaller perfect matching still has to match them, right?
Yes, yes, yes.
Yeah. So this is because sigma prime has a smaller size n minus one. Yeah. So also if sigma prime is a perfect matching in G prime, then sigma prime union E is a perfect matching in G. So my claim is this shows that sigma prime minus E is a unique minimum weight perfect matching. Okay, why is this true?
So is a perfect matching in G, and so therefore the sigma star is a unique minimum weight perfect matching in G prime. Uh, yes. So yeah.
I try to prove this by contradiction. So suppose there was another sigma prime. So that
Mhm.
sigma prime and sigma star minus E had the same weight. Then what would happen?
So if we have sigma prime minus E as the uh,
No, no, okay. Sigma prime is a perfect matching in G prime. So sigma prime minus E is just sigma prime. Okay, so what I am saying is, so I am claiming that sigma star minus E is a unique minimum perfect matching in G prime. So let me go claim by contradiction that sigma prime, which is also a perfect matching in G prime, has the same weight as sigma star minus E. So both of these are perfect matchings of G prime. I'm assuming that both of them have the same weight. And this weight is minimum. Then what goes wrong? Okay, let's do it like this. Okay, reason
So actually, this gives me something similar to what we used to what we used to do in the Prim's algorithm. Yeah. So
Oh yeah, the idea is similar.
yeah, something similar to that.
Yeah. So reason, suppose that sigma prime is a perfect matching in G prime with weight of sigma prime less than or equals to weight of sigma star minus E. So we want to prove that no such sigma prime exists, right?
Yes.
Yeah, because okay, so what are we claiming? This has the unique minimum is the unique minimum weight perfect matching, right? For this,
Yes.
three things should happen. This should be a perfect matching, which we have shown it is, right?
Yes.
Yeah. It must have the minimum weight. So for any sigma prime, this should happen, right?
Why so?
Oh, so if I say that sigma star minus E has the minimum weight, then every other
Mhm.
perfect matching cannot have no perfect matching can have a smaller weight, right? So every perfect
Yeah.
matching's weight is greater than equals to the weight,
Right. Right. Right.
right?
Yes.
But now I want to claim that this is the unique minimum weight perfect matching. So this greater than equals to must become less than.
Mhm.
Yeah, so I want to prove that this is true. So by contradiction, I'm assuming that this is true. Because this is a negation of the previous statement, right?
Yes. Yes.
Yeah, because if this statement were false, this would mean that this is true, which is exactly what I want. Sigma star minus I is a perfect matching, and every other perfect matching is a strictly larger weight.
Yes.
Right.
Yes.
Yeah. Okay. So let's suppose something like this exists, right? Then uh, sigma prime sigma prime union E or disjoint union E, because E is not present in sigma prime, is number one, perfect matching in G, right? This comes from this thing. I take any perfect matching in the smaller graph, add E, I get a larger perfect matching, right?
I forgot the meaning of this notation. You told me last time uh, this
Uh,
notation which we used here.
just a second. Let me check in this. Yeah, which notation?
This notation, this plus thing here, and half circle and
Oh,
this
okay. Yeah,
plus.
yeah. Oh, so this means disjoint union.
Oh yes,
Yeah,
yes,
so union where this and this set are disjoint.
yes, yes.
Yeah. Okay, so sigma prime disjoint union E is a perfect matching in G. Moreover, let's look at its weight in G. So this weight is just the sum of the weight of sigma prime and WE, right?
Yes.
But we know that since sigma star is a unique minimum weight perfect matching, oh sorry, this. Yeah, since sigma star is a unique minimum perfect matching in G, this weight must be greater than the weight of sigma star, right?
Yes.
But what is the weight of sigma star? The weight of sigma star is the weight of sigma star minus E plus WE, right?
Weight of sigma star is equal to the weight of sigma star minus E plus the weight of E. Yes, right, right.
Yeah, so now I can cancel these two out and I get
Yes.
that weight of sigma prime is strictly greater than weight of sigma star minus E.
Right, right, right.
A
So yeah,
contradiction, right? Yeah.
right.
So something like
Yes.
this cannot exist.
Yes, yes,
Yeah,
yes.
so sigma star minus E is a unique minimum weight perfect matching in determinant of, sorry, in G prime. Okay. Therefore, determinant of Mij. So what does this look like? This looks like 2 to the weight of sigma star minus E times an odd number. Yeah, because in observation 2, we saw that if unique minimum weight perfect matching exists, then the largest power of 2 dividing the determinant is 2 to the weight of that unique minimum perfect matching, right?
Yes, yes.
Yeah, so over here it's sigma star minus E, so it's this, right? So this looks like 2 to the W. Okay, let me write one more step. And this is 2 to the W, which is the weight of sigma star, over 2 to the WE times an odd number. Right.
Right, right, right.
Okay. And therefore, what were we checking? Determinant of Mij times 2 to the capital, 2 to the small w. So what is this? This is like these two cancel out and these two cancel out, right? So this is just an odd number. Yeah. So is this fine?
Yes. And is this algorithm known as the MVV thing or what?
Yeah. Mulmule Vazirani.
So I have a slightly related question
Yeah.
here. That this entire proof is so very tricky. So what
Hmm.
happens usually in the research or in research in the theoretical computer science, that how do people, I mean, reach to such a conclusion? I mean, through discussion or through what?
I don't know. So I think it depends on problem to problem. Sometimes you figure out something on your own. Sometimes something comes up in a discussion. Yeah, sometimes it's trial and error. A lot of things can happen. Like there is no like fixed way to come up with a solution.
Okay,
Like
okay,
I have been in situations where things came up with during discussions. I have been in situations where someone was doing something and suddenly realized something would work. Yeah,
okay, okay, okay.
yeah. Okay, but this doesn't complete the proof. This just proves one part of it. So we
Yes,
assumed that E was in the unique minimum perfect matching. Then the this determinant is odd, and therefore E would be added to the to PM, right?
yes, yes,
But now we need to show that if something is not in the perfect matching, the unique minimum perfect matching, then it would not be added to PM, right?
yes.
Okay. And yeah, okay. So how do I want to do that? So it's not in the unique minimum perfect matching. So if I remove it, I and they are connected to something else. Okay, I want to prove that this has a larger power of 2. Okay, so this is not in the perfect matching. I've removed that, and therefore I've removed 2 extra edges. No, that's not. Okay. Yeah, have I defined sigma star? Oh yeah, sigma star is unique minimum perfect matching. So let's say E is not in sigma star. Okay, so first question, when I remove E, can the resulting graph still have a perfect matching?
So even if I remove E, then the resultant graph must have a perfect matching. Then only the inclusion of E would result into a perfect matching.
Yeah, okay, no. So, okay, so E is not in the unique minimum perfect matching. So E
Yeah.
might be in some perfect matching, E might not be in some perfect matching, right?
Oh, I see. I see. So quite
Yeah,
possible that E could be there in some other matching. Quite
right. So
possible.
Then if you remove it, yeah, so if you remove it, you would still have a perfect matching, right? If E was in some perfect matching.
So if I remove E from here from the sigma prime, then the remaining things would still remain a perfect matching. No issues with this.
If E were in some perfect matching, right? If E were in no perfect matching, then anything could happen, right?
Okay, so if E is there in some other matching, so how will it affect the conclusion? So now since since E is a part of the sigma star, so
Okay, so
yes,
over
in
here
sigma
I'm
star.
assuming E is not in sigma star. So
Okay,
previously we assumed E was in sigma star, so it was included. Now I want to prove that if E is not in sigma star, it's not included.
yes. So if E is not included in sigma star, quite possible that it could be the part of some other perfect matching. Like in the example
Yeah.
you gave.
Yes, it can be part
Yeah.
of some other perfect matching. So in that
Yes.
case,
Yes.
what happens when you remove E? Does the resulting graph still have a perfect matching?
Okay. Okay. Yes. Yes. So yes, that would also have a perfect matching only because individually every age is contributing to the perfect matching, and if we remove an age from that mapping, the remaining mapping would still remain a perfect matching only.
Right. Okay, so over here I can further divide it into two cases. E is in some perfect matching, E is in no perfect matching, right?
Okay. Okay.
Yeah, so suppose E were in no perfect matching. Then uh, when I remove I and J from the graph, can the resulting graph still have a perfect matching?
Uh, so since E is not the element of any of the perfect matching, and if I remove I comma j
No,
from the
I'm not
graph.
removing I comma J, I'm removing the ith vertex and the jth vertex, right? So I'm removing the entire vertex to both the vertices, not just the edge.
Okay. Oh yes, yes. So that will remain a perfect matching only. Where is the
No,
issue
no,
in
so
that?
okay, there is no perfect matching to begin with. So E is part of no perfect matching. That's my first assumption.
Okay. Okay.
Yeah. Okay. You cannot have a perfect matching because suppose you had a perfect matching sigma prime, then we saw that sigma prime union E is going to be a perfect matching of G, right?
Yes.
But assumption was does not E prime doesn't belong to any perfect matching, right?
Mm-hmm.
So sigma prime cannot exist because if it existed, E must belong to sigma prime union E,
Yes. Yes. Yes.
right? Okay, so again, two cases. Yeah, then G prime has no perfect matching, right?
E does not belong to any of the perfect matching in G. Then
Yeah.
G prime has no perfect matching. Yes.
Right. Thus, a determinant of Mij.
Is
So
equal
what
to
is
0.
this? Yes.
0.
So and this is an even number, right?
Yes. Yes. Yes.
Yeah. So uh, yeah, I should write this. Yeah. So is not added to set PM, right? Yeah. So far we have shown that every edge in the unique minimum perfect matching would be added to PM. We have also shown that if an edge does not participate in any perfect matching, it won't be added to PM.
Yes.
But we still need to show that let me call it sigma hat, which is not the same as sigma star. Okay. So we also need to show that this doesn't happen.
Okay, so if E belongs to some perfect matching, say sigma hat, and which is
Mhm.
not same as sigma prime.
Right.
Okay, so if I remove E, if I remove E, uh, so then that would still result into a perfect matching only.
Yeah. So you would have a perfect matching. But now what
Yes.
do I want to show? I want to show that determinant of Mij times 2 to the We over 2 to the capital W. This number would be even. That's what I want to show.
Okay. Okay. Yes. Yes.
Right.
Yes.
Okay. Yeah.
Yes. Yes.
Okay. So, okay, but so since sigma hat is not equals to sigma star, weight of sigma hat is strictly greater than the weight of sigma star, right? Because sigma star is the unique minimum weight perfect matching, right?
Yes.
Okay. Okay, now how do I want to write this? So I want to say the follow. Okay, but okay. There is no way to explain this in words. I'll have to write the equation. Okay. Claim is this. So no, divided by no, not this. Oh, wait, yeah, sum first. Yeah, sigma hat. Oh, no, sigma hat is not a. I should write sigma prime. Sigma prime is a smaller permutation. Okay, so my claim is determinant of Mij looks like this. So let's parse this. Okay. Okay, so what does determinant of M look like? I just need to remove these two conditions. That will give me the determinant of M, right?
Yes. Yes. Yes.
Yeah. So what am I saying now? So I obtained G prime by removing I and J from G, right?
Yes, but then here I have confirmed that this sigma I has to be equals to J only. I mean,
Yeah,
by taking
right.
at the
Yeah,
time of taking the summation. Yes.
yes. So what am I doing? So what am I saying is the following. There is a one-to-one correspondence between the perfect matchings in G prime and the perfect matchings of G containing E.
Right.
Right. Yeah, so that's what this equation is saying.
Right.
So now my claim is the following. Okay. Yeah. Okay. Okay. So now, okay, let me first do like this. Let me suppose that I for some reason multiply this entire quantity by 2 to the WE. Okay.
Yes.
Then if I look at this product, what would I get? I would get 2 to the weight of every perfect matching containing E, right? Every perfect matching of G containing E, right?
Uh, yes, that is not understandable. Why?
Oh,
I
so
mean,
over here, okay, so what's the weight of every perfect matching containing E? It's 2 to the just 2 to the weight of sigma, right?
yes.
Yeah. And over here, I am computing this product, but this product would end up becoming a sum of this form, right? I comma sigma I. Oh, sorry. Uh, 2 to the sum over I in. Okay. What am I doing? I should write something else than I, right? Because I is. Yeah, I should use some other index K. Let me say. Because I is fixed. Yeah. Okay. So this quantity is the same as 2 to the sum over K in L minus I. Oh, W of K comma sigma K, right? So in this sum, I have everything except WE, right? For that perfect matching, for the perfect matching sigma.
yes.
Yeah. So I am summing up the weights of all the edges in the perfect matching except the weight of E. And the weight of the perfect matching would be obtained by putting WE as well in the sum, right?
Yes.
Yeah. So if I were to multiply by 2 to the WE, I would get that this thing is this product. Okay, so this entire sum is basically the sum of all the weights corresponding to all the perfect matchings which contain WE, right?
Yes.
Right. So if I multiply it by this, I would get that. So let's forget this for now.
Mm-hmm.
My claim is the determinant of Mij times 2 to the WE is 2 to the capital W times an even number.
Yes.
Why? Because E does not belong in sigma star, right? So any perfect matching containing E must have a larger weight than the weight of sigma star.
Yes.
So the weight must be at least W plus 1, right?
Yes.
So when I write it as 2 to the something, it would be 2 to the W plus 1. So 2 to the W times 2 times some number,
Mm-hmm.
right? So it's 2 to the
Right.
W times some even number,
Yes.
right? That was 2 to the WE times determinant of Mij, right?
Yes.
So all I have to do is bring this in the denominator, like bring this from here to here, and I get this equation.
So, but then from where did you get this equation? I mean, from where did you get this capital W here? After this
Okay.
step, after computing the determinant thing, probably you took this equation from some of the previous result or what?
No. Okay. So as we saw, if I multiply 2 to the WE over here, this thing, so if I multiply 2 to the WE over here, each and every one of this product corresponds to the weight or 2 to the weight of some perfect matching containing E, right?
Yes, yes, yes.
Right. Now, we know that E is not in sigma star, so no perfect matching containing E has the minimum weight, right?
Yes.
So the weight of, now the minimum weight is W, right? Capital W.
Yes,
Okay,
that's
so
fine. But then this is capital W and not the the smaller one. Capital W used to be the maximum power of two, log of the maximum power of the two. That thing.
right, so log of the maximum power of 2, which divides determinant of M, and from observation 2, that's the weight of the unique minimum perfect matching. So that's the weight of sigma star, right?
Oh yes, yes,
Yeah, yeah,
yes. Now I
yeah.
understood. Yeah, right.
Oh, so you were asking if I'm using observation 2 or not.
Yes, yes, yes.
Okay,
Right.
yeah, yeah.
Yeah.
Yeah. So from observation 2, W is that weight, right? The weight of the minimum unique minimum perfect matching sigma star.
Right, right, right.
Right. So when I multiply 2 to the WE over here, this product, yeah, when I multiply 2 to the WE over here, this product is the weight, or 2 to the weight of every per to the weight of some perfect matching containing E. But since E is not in sigma star, this weight must be more than W, right? More than capital W.
Mm-hmm. Mm-hmm.
Why? Because, okay, this is the weight of some perfect matching, but that perfect matching is not sigma star. So that perfect matching is not a
Yes,
unique minimum weight
yes.
perfect matching, right?
Right, right, right.
Yeah.
I understood.
So its weight must be at least W plus 1,
Right, right.
right?
Yes. Let us
So
assume.
2 to the WE times the determinant is 2 to the W. Okay, so what does it look like? It looks like this sum times this quantity, right? Over here,
Yes.
everything is at least W plus 1,
Yes.
right? So I can write this entire sum as 2 to the W plus 1 times some number, right? I take 2 to the W plus 1 common from every term,
Yes.
right? So I am left with 2 to the W plus 1 times some number, but I write 2 to the W plus 1 as 2 to the W times 2 times some number, right?
Yes.
But 2 times some number is an even number. So that even number
Right.
is here.
Yes.
And
Yes.
then I just bring 2 to the WE over here. So
Right.
where am I getting this W? I am getting this W from W plus 1. And where am I getting W plus 1? The weight of everything is at least W plus 1.
Yes.
Right.
Yes.
So is
Yes.
it fine now?
Yes. Yes.
Yeah.
I
So
understood.
in this case, this thing looks like this. So what are we checking? We are checking that determinant times 2 to the WE or 2 to the capital W. So therefore, determinant of Mij times 2 to the WE over 2 to the capital W. So this is an even number, right?
Yes, this would be an even number.
Therefore, so this was the check we were performing before adding anything to PM, right? So the check is add to PM if and only if this number is odd, right?
Yes.
So this E won't be added to PM, right?
Yes. Yes.
Yes. So what have we shown? We have shown that in the first part over where? Yeah, over here. We showed that if E belongs to sigma star, the unique minimum weight perfect matching, then E is added to PM, right?
Yes.
Over here, we showed that, okay, so we now know that at least PM is a superset of sigma star, right? After this
Yes.
point. I need to show that it's exactly sigma star. That is, it does not contain any other edge, right?
Yes. Yes.
So now let's look at any edge not in sigma star. Two options. It's either not in any perfect matching or it is in some perfect matching other than sigma star,
Mm-hmm.
right?
Mm-hmm.
Over here, we show that if it's in no other perfect matching, then the determinant would be 0 and even number, so we won't add it.
Yes.
So now the only thing remaining is edges which belong to some other perfect matching other than sigma star, right?
Yes.
And that we showed that even those E's won't be added.
Yes. This is
Yeah.
not going
So
to be added here.
right.
Yeah.
So now PM is exactly sigma star.
Right.
Yeah. So PM is sigma star, and we are done, right? We outputted a perfect matching.
Yeah, but then this result seems to be so unrealistic that you would be having just one perfect matching and that too unique, and which has got the minimum weight. So I mean, so what do we want to prove? That does there exist a unique minimum weight perfect matching, or
No, no,
does
no.
there
Okay,
exist
so let's look at the claim.
does there exist a unique perfect matching?
So the claim said that if G has a unique minimum perfect matching, so it was assuming that G has a unique minimum perfect matching, right?
Oh, I see.
Then
Yes.
you would only find, then you would only output that perfect matching,
Yes.
right? So now the question is, how reasonable is the assumption that G has a unique minimum weight perfect matching, right? That's your question.
Yes. Yes. Yes.
But recall that we saw that if you were to pick weights like this,
Mm-hmm.
then with probability at least half, then with probability at least half,
Mm-hmm.
uh, the graph has a unique minimum weight perfect matching,
Okay. Okay.
right? Why?
Yes.
Because of the isolation lemma, right?
Yes.
Yeah. So let me just summarize this.
Can you recall the statement of the isolation lemma once again?
Oh yeah, I'm going to prove it next. So I have it over here. So the statement is this. Okay, so a set system U comma F. Okay,
Yes.
let me do this. Let me just summarize this, assuming that isolation lemma gives me a unique minimum weight perfect matching, and then
Okay.
I'll move on to
Okay.
proving the isolation lemma. Then I can recall this, right?
Yes. Yes.
Yeah.
Yes.
Okay, so let me just summarize it. So sorry, claim. Yeah, so then claim 4 implies that PM is a unique minimum weight perfect matching with probably at least half, right?
Yes.
So our algorithm outputs a our algorithm outputs a perfect matching with probability at least half. And what's more, that perfect matching is actually the unique minimum weight perfect matching, right?
Yes. Yes.
Yeah, so we are not saying that the graph has a unique perfect matching, rather it has multiple perfect matchings. But when you give every perfect matching a weight the way we gave it weights, i.e. randomly, then the graph has a unique minimum weight perfect matching with good probability, and we find it, right?
Yes. Yes. Yes.
Yeah. So the graph can have as many perfect matchings as it wants. It's just that when you do it like this, only one is sort of singled out.
Yes.
Yeah. And okay, before I move on to the proof of isolation lemma, let me just remark this one thing. So let's see what we are doing in the algorithm, right? So we are picking some random numbers, assigning a random like 2 to the WE to XE, computing the determinant, and then running this loop, right?
Yes.
That's the only thing we are doing, and computing W as well. But computing W is very efficient. It just takes logarithmic time, right? Because you just need to write this thing uh, in bits and read off the number of zeros. So now let's look at this. So now, okay, suppose instead of just one processor, I had many processors, right?
Mm-hmm.
Then let's say I had as many processors as there are edges in the graph. Then
Yes.
I could have used different processors, like to pick WE. For every E, I could have used a different processor to pick WE, right?
Yes.
So if I choose just one processor, this takes time to the, okay, this takes the time size of E. But if I use size of E processors, then this takes time order 1, right?
I could not understand this. Why
Okay,
order
so
one?
I have as many processors as there are edges, or let's say, okay, I have more processors than there are number of edges. So I use a different processor to compute WE for every E. I can do this in parallel, right?
Yes, yes.
So I can start at time t equals to 0 on every processor. In processor
Mhm.
1, I would be done in time, let's say 10 seconds. And in processor 2, I would be done in time 10 seconds for the second edge and so on, right? But the total time is still 10 seconds
Right, right.
because I did this in parallel, right?
Mhm.
What I'm trying to show is that this is a parallel algorithm. That's it.
Okay. And we are trying to show that this is the better algorithm or what?
No, no. So what we are trying to show is that this is an efficient parallel algorithm. That is, if I have
Okay.
multiple
Okay.
processors, then I don't need polynomial time. I only need logarithmic time.
Okay. Okay.
Yeah. So if I have multiple parallel processors, this is order 1 time, right? Step 1 is order 1
Yes.
time. Okay.
Yes.
Now computing 2 to the WE is also order 1 time. Sorry, it's also logarithmic time because I need to do 2 square, 2 to the 4, 2 to the 8, and so on, right?
Yes.
So I can compute this in time like log WE, which is log n square, which is order log n, right?
How can I compute such powers of two in this time?
So 2, 2 square,
Yes.
2 to the 4, and so on, right? So in the ith step, I'm computing 2 to the 2 to the I.
Yes. Yes.
So now 2 to the I must be WE.
Yes.
So I is log WE.
Right. Right. Right.
And it only took
Yes.
me log WE like time, right?
Right.
Yeah. So this is also order log n time. And okay, I won't prove this because this proof is very non-trivial, but we know that determinant can be computed in time log square n. So the determinant of an n cross n matrix can be computed in time order log square n, provided you have like n to the 5 processors.
Because we saw that to compute the determinant through single processor
Yeah,
requires an effort of the order of n cube.
right.
Of the order of n cube, correct?
Yes.
Was it something else? It
Order
was
n
n
cube,
cube
order
only,
n cube. Yeah.
order of n cube. And now, since we are using the multiple number of the processors, so can this really be done in an effort of the order of log n or what?
Log square, yes, but the number of processors has to be large. I think it has to be at least order n cube.
Oh, I see.
Yeah, because if it was less than order n cube, then just simulate all the processors in series on a single processor, right? Yeah, so it has to be more than n cube. I think it's n to the 4 or n to the 5 or something like that. But the point is, if you have large enough number of processors, you can do this in parallel
Okay, okay.
in order log square n time. So all of these steps are at most order log square n time. Okay, now let's look at the second part of the algorithm. Yeah, so again, we saw that W can be computed very efficiently, right? Write down the bits, look at the number of zeros. That's it.
Yes.
So this is also like order log n, just the number of like just as much time as it takes you to write down W on a single processor
Mhm.
and read off the number of bits, right? So that's order
Yes.
log n. Yeah, this is just nothing. It's order log n. Okay, now here's the main thing. Again, I have at least as many processors as the number of edges. So instead of running this loop, I can do steps 8 and 9 in parallel on different processors.
Mhm. Mhm.
So like I would run this. Okay, how many iterations does this loop have? Size of e many iterations, right?
But then 8 and 9 instructions cannot be executed on the different processors because, you require a common value here, MIG.
Yeah. Okay, so what am I saying is I would group. Okay, so 8 and 9 are executed size of e many times. What I would do is for each of these times, I would group 8 and 9, execute them on the same processor. So for one
Oh,
edge,
yes.
8 and 9 are executed on the same processor.
Yes, yes. Then it's
Right.
okay.
Yeah. what does A do? It just takes M, remove something from it, right? So you don't need to physically remove it. You can just ignore it.
Yes.
I don't need to like remove it from memory. I don't need to zero it. I just ignore it. Don't look at it.
Yes.
While computing the determinant, right?
Yes.
Again, this determinant can be computed in parallel using order log square n time.
Yes.
These two can be computed efficiently, and the multiplication can also be done. Okay, this is also a fact. I won't prove it. That you can also do multiplication in parallel using order log square n time.
Right.
Yeah. So, like these e-many iterations take order t time if every iteration takes t time, right? On different processors.
Mm-hmm. Mm-hmm.
And what is t? T is order log square n.
So I have a question here: that
Yeah.
do we use the same RAM framework which we used to, which we use when we analyze the complexity of an algorithm for the
No. So over
parallel
here, the
algorithms as well,
framework is
or
different.
something
So
else?
every process, there are like multiple frameworks over here. Every processor has its own memory, or they have a shared memory, or they have their own memory and shared memory. There are multiple different frameworks over here. But yes,
Okay.
regardless of whether they have a shared memory or not, the memory is randomly accessible.
Right.
And over here, in
Yes.
fact, we are using shared memory. Because,
Okay.
for example, I computed M. M is available to everyone,
Mm-hmm. Mm-hmm.
right?
Mm-hmm.
Yeah. So over here, the model is okay. I won't go into the details, but the model is this: multiple processors, all of them have a shared memory, all of them have random access to that memory.
Mm-hmm.
Yeah. So in that
Yes.
model, the running time is order log square n if you have
Mm.
large enough processors. Like, so if you have poly n processors, then the running time is order log square n.
Yes.
Yeah. Okay. So let me write this. Yeah, I won't write the entire proof. It's too long, but note. Okay, maybe I'll go. Yeah. So yeah, it's randomized, but in order log square n time, right? I'm ignoring the randomization. Yeah. So is this fine?
Yes. So if we have a Polyn number of the processors, then the MVV
Mhm.
algorithm can be executed in the effort of the order of log square. Yes,
Yeah.
understandable. Yeah.
Yeah. So this tells us that perfect matching has a parallel algorithm, but we don't believe that everything that has everything that has polynomial time algorithm has a parallel algorithm. We don't believe this. So we
Yes.
believe
Yes.
that there are some problems which have polynomial time serial algorithms or sequential algorithms, but they do not have polylogarithmic time uh, parallel algorithms with only poly n processors.
Yes.
Yeah.
Yes.
And yeah, this is essentially the P versus NC problem. So we don't believe that P and NC are the same. We believe they are different.
Okay. Okay.
Yeah, because every processor, okay, what's a processor? It's just what does a processor do? It just does a bunch of Boolean operations, right?
Yes. Yes.
So replace these processors with the Boolean operations they do. That gives you a poly-sized circuit with log square n depth, right? Or okay, log square n times some constant because I'm expanding that processor into a circuit. But yeah, fine. So this
Yes.
gives you a order log square n size circuit with order log square n depth circuit with poly size, which is NC2, right?
Yes.
Yeah.
Yes.
So we don't believe that everything has a parallel algorithm. In particular, we don't believe that linear programming has parallel algorithm. But yeah, perfect matching does have parallel algorithm. A randomized parallel algorithm, but still.
So what is the? What is the complexity of the simplex algorithm?
Oh,
People
simplex is
use.
exponential.
Okay. Okay.
Yeah, but okay.
Exponential in terms of what? Number of
It's
decision variables or something else?
no exponential. Okay, its running time is polynomial in a time in the number of edges of the polytope. So
Okay.
it depends on the polytope because, for example, some polytopes would think of the Boolean hypercube, right?
Mm-hmm.
So 0, 0, 1 to the n. Think of that polytope. That polytope has as many uh, edges, sorry, as many vertices as the number. Okay, so the number of vertices is 2 to the n, right? N is the number of variables,
Yes, yes.
and the number of constraints is just 2n. Xi between 0 and
Mm-hmm.
1 for everything, right? So the number of variables is
Mm-hmm.
n. The number of constraints is 2 to the n. Yet the polytope has 2 to the n vertices, right?
Mm-hmm.
So
Mm-hmm.
some polytopes can have exponentially many vertices, and since simplex runs in time linear or at least linear in the number of vertices, its running time can be exponential in the number of constraints and
Oh, I
variables.
see.
Yeah,
Yes, yes,
but
yes.
yeah, you are right. In practice, it runs in a short time.
Yeah,
Yeah, that's why people use it.
yes.
Yeah. Okay, so we are over time. So this was supposed to be today's lecture again. So I'll make this lecture 10, and we'll do this tomorrow. Yeah.
Okay, yeah. And so tomorrow, the proof of the isolation lemma and the
Okay, so one thing we'll do is check. So we'll see a randomized algorithm using Schwarzschild lemma to check if two strings are the same or not. And we also left out one thing. What was it?
a cryptographic that primality testing algorithm which we use in the cryptography.
Yeah, yeah, yeah.
Some
Okay.
Miller thing, if I remember.
Yeah, yeah. So yeah, before that we left this out. Checking if two sets are the same using Schwarzschild. So
Yes.
tomorrow we'll do two things. Check if two sets are the same using Schwarzschild. Check if two strings are the same using some randomized algorithm. So over there I won't use Schwarzschild. Okay. Over there I'll give two algorithms, one using Schwarzschild, one not using Schwarzschild, but fine. So
Okay.
these two
Yeah.
randomized algorithms to check that two sets are the same, two strings are same. Proof of the isolation lemma. And
Yes.
in the next week, so the next week is the last week. So in the first lecture, we will do that primality testing algorithm.
Yes.
In the second week, we'll do something else. In the second lecture, we'll do like randomized approximation algorithms for NP hard problems.
Okay. Okay. Yeah.
Yeah. And yeah, tomorrow, if we can't complete both of these, like checking for strings and checking for sets, we'll do only one of them. And the rest, the second, we'll forget about it.
Okay. All right. Yeah.
Yeah. In
Sure.
particular, I want to do this because, so like as I mentioned, like you use like you need to pick prime numbers a lot in cryptography, but so this gives you an example. So this would give you an example that you also need to pick prime numbers for in the algorithm design. So basically, what would end up happening is we would need to find a small prime inside this algorithm.
Yes. Yes. Yes.
So like while analyzing this, we would assume that you can find a small prime efficiently. Then we would show how to find the small prime efficiently.
Yeah. All right.
Okay. Yeah. And okay, so in the next week, when do you want to have a problem solving session? So we can do two things. So okay, like are you attending the classes for the other course?
Yes. 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 I'm attending. Yeah.
Okay. Otherwise, we could have done like otherwise the next Saturday we could have done a course. We could have done a class from 5 to 7:30 for the
Okay. So yeah, from so I'm not doing a course on computational geometry, but then I'm doing some other courses. So like recently, I have started one course on the this concentration inequalities.
oh yeah.
So yeah, so wherein there could be a extra class on the Saturday. So maybe because of that.
Okay,
But
so
yes, so if you plan a class on the Saturday, then yeah, I'll give. So I'll
sorry,
attend
sorry,
this
sorry. Okay, no,
class.
okay, not Saturday, not next Friday, next Friday. Sorry, yeah, yeah.
Okay.
Yes, okay. What I want is next Friday we can have a class from 5 to 7:30.
Yes. Yes.
Like in the first 1.5 hour, I can cover the Miller-Rabin primality test. The next
Yes.
1 hour, we can do a problem solving session. Like we can take a small break in between and then do a problem
Sure.
solving session.
Yes.
Yeah.
That would be good. That would be good. Yeah.
Yeah. And then on Sunday we'll just do that randomized algorithm, like randomized approximation algorithm for NP-hard problems. Yeah.
Yes. Sure.
Yeah. Okay. So I'll announce this in the group that we next Friday will meet from 5 to 7:30 with a short break from, let's say, 5 to 6:30. Yeah. So short break from 6:30. Okay.
Yes.
Yeah.
Yeah.
Okay.
Thank you.
Yeah.
Thank you so very much. Yeah. Thanks, Ethan.
Yeah.
Bye
Thanks.
bye.
See
Good
you
night.
tomorrow. Bye. Let me stop the recording.